Okay, because this actually was found in the radiation decaying. It's in the way that they found in the experiment. And the bottom, no. The bottom actually is kind of organizing, helping to the organization, like ruling something, then is not really found in the decay. Then was not found in the same situation. The strength were found in some specific experiment when the time of the decay was too big to be normal, like, oh, it's taking more time than the normal. Then they call that strength. That doesn't happen with the bottom. The bottom is more like organized, then it's moving here, there, this is why it's like pumping out, like, kind of like that. Okay? Okay, another important thing that's coming out about after the discovery of the neutron is something called the strong force. Actually, the strong force is the stronger one for all the forces that we know, that are, the gravitational, the electrical, these are the strong one, but has a big weakness. Did everybody or somebody know what is the weakness of the strong force? Exactly, it's really a small range of action. Then it's acting in the femtometer, like 10 over minus 15. That is actually inside, like, is you thinking it's inside the atom, and actually is, this distance is less than 1 femtometer. For example, you had 0.7. This distance is enough to break the nucleus. This means cannot be so small also, because then you had nothing, you had dissociation. But if you had 2.5 femtometer, then you are gonna have nothing, because the force is gonna leave, then it's not gonna be there. Then also this concept came after the neutrons. Okay? Okay, with this then they were beginning to understand better how was the form of the nucleus and the different size, using all the information that they were doing in the experiment. Then we had some relation, for example, between the rate of the decay, and we see that the Fermi distribution for the nuclear charge density can be described. It's describing for this relation. You see that depends on the inverse of the exponential. We had this distance, and we had an initial density. That is, we plot, we're gonna find the relation. Then we have the maximum value is gonna be 1 when the density is density over density 0 is equal to 1. Half of the portion, 50% of the density is gonna be in one distance called R. It's technical R. And we have one distance T when practically everything is going down. This means after that you have no really high density. Yeah, then we had this different range. Then we had this one when it's practically constant. We had this one that is decaying very quickly, and this one that is really small in the end. Okay, after that, one other important thing is talk about the spin. But first, they begin to describe what was the shape of the different nucleus and the nuclear shape. They decide, okay, can be represented by a sphere. Then you know the sphere is 4 over 3p r03. And then we had this dependence, and this thing helped us to understand how is the relation with the mass and the volume also. We had the different spin, if you remember, how much is the spin of the electron? Did you remember? Exactly, it's half. Yeah. Okay, now I'm gonna do a question for you. What do you know about magnetic moment? I think that you saw this in the chapter, one of the last chapter. Did somebody have any clue? Okay, then actually the magnetic moment is kind of giving us information about how is happening the rotation also in the system. For example, you had an electron, he's having their own rotation, but you had also the spin. Then it's gonna be more faster. And this one depends also on the mass. In the case of the neutrons and the proton, then it's gonna depend on the mass of the proton, it's gonna depend on E and H again. And now, we can compare with the other values that we had related with the atom. We had that for the proton, we had 2.79. For the electron, it's negative. Why do you think that is negative, this value for the electron? And why for the proton is positive? Exactly. Then this means that this magnetic moment is also dependent on the charge. Then if we have negative charge, then the magnetic moment is going to be negative. And for the neutron, we have also that is negative. It's neutral, but to compensate need to be negative and it's going in the opposite direction. Okay, now then we can talk a little more about how we can use this application to something that we can use today. For example, in the nuclear magnetic resonance. Did everybody listen about this before? You heard about that? Okay. This can be used, for example, for medical application. I don't know if you already listened this nice thing about how the fMRIs are working, that you had some magnetic field. Yeah, for example, in the fMRIs, you had some external magnetic fields that are constant and is big like 3 Teslas, for example, but actually some people are doing bigger, like 17 Tesla, but the normal value is like 3 Tesla. And here, then we had some small variation of magnetic field that is like 0.5 Tesla. Then what happened? Happened that our body has a lot of water. And then what happened with the water? The water also had oxygen that also had electrons. And also in the nucleus we had the protons that they had charge. Yeah, then we had proton with charge. And one important character is when we had magnetic field is that if we had something, it's gonna align. If something had the charge, it's gonna align in the direction of the field. For example, if initially you had something like that in other direction, and then suddenly I apply a magnetic field, then what is gonna happen? Everybody is gonna try to align with the magnetic field. Yeah? Then it's something that the magnetic field is gonna do, is trying to align in this direction, everybody. Or anti-parallel, but it's gonna be practically in this direction. Then this means that the magnetic field is gonna kind of do what is happening inside. Now what happened? With this variation, then we can have also, if we change another magnetic field inside, then we are gonna have some protons that are gonna be spinning around some areas. And when they are spinning, if we put a radio frequency, some of these radio frequency are gonna give some extra energy. This is the minimal energy. The minimal energy is there, everybody is going with the magnetic field, and you don't need to worry because you are in the minimal energy and everybody is happy with the magnetic field going. But if suddenly a radio frequency is coming with a lot of energy, something can happen. For example, we can flip this charge to other direction because we have an extra energy. But this in time 0, for example, after we apply the radiation, this is going to happen. But as time is going, then this energy is being losing. Then you are going to send this energy out, and in some point after some time, this is going to come back to align to the position of the magnetic field. But then what happened? When we are here, when we flip the proton, then we are sending this information that is going to have some radiation. Then a machine is going to read this information and it's going to say, oh, this guy is flipping here. And then it's going to do in the computer a point or something. Yeah? And then if you move this and you do the same, then you are going to begin to have some different colors and you are going to map something. Then this is how they do in the brain, for example. They put this machine, they begin to, we had a lot of water, then they are gonna flip the protons, and then the protons are gonna be flipping, sending information, the information is catching for the computer using Fourier transform, and then you have these brains with different sections showing where activity, where they were more charged. Then you can see, oh, in this part they have more activity. And then if you do an strength pull, for example, if somebody is pinching you or you put some electric shock, then some part of the brain are acting. Then you say, oh, in this part of the brain you have more activity or something like that. Okay, any questions? Okay, then now is we come back with the deuterium. Did anybody remember what is the deuterium? With the first slide? Yeah, then we had exactly. Then the mass of the deuterium is 2 times the one that we were having before because we had the proton and the neutron, no? Then it's gonna be 2 times, then it's 2.01355 U. The mass of the deuterium atom then is 2.1, and the difference between the deuterium mass as the mass of the deuterium atom with the protons and the electrons is 0.0000549. That is actually the mass of the electron. But then I like you to notice something interesting. You see how small is the electron mass? Then you can see how is big the dependence with the mass, has a lot influence, and the electron is just a small quantity. Now, if we do balance of the mass, we are going to have the mass of the deuterium equal to the mass of the proton plus the mass of the neutron minus this quantity that, what do you think that is this quantity? Because actually in the nucleus you have proton, neutron in the center. And this extra force is the force that is going to keep them together, like the bonding. Like this is the force that if you give this energy, boom, the proton is going to leave. Then this energy is necessary to keep the nucleus together there active. Okay, now if we add the mass of the electron, we are going to have the total mass of the atom. That is going to be the deuterium nucleus plus the electron, then we have this relation. And we can begin to play with these values. Then we have the mass of the deuterium, mass electron is the atomic deuterium mass that we are going to call like this, M2H. And the mass of the proton mass electron is the atomic hydrogen mass with only one proton and with no neutron. Then that relation is going to be the atomic deuterium mass equal to the mass of the neutron plus the mass of the hydrogen atom minus the bonding energy. But then we are interested in finding this value because you like to see how much is that. Okay, now we have the mass of the neutron is 1.00866. We have the atomic hydrogen mass that is 1.007. The deuterium mass that is 2.014 something. Then if we isolate this quantity, we are going to find the value for the center that is 0.0023 summa. That transfer in energy, in the energy that we know is going to be 2.224 mega electron volts. It's high, no? Like it's like mega electron volts, it's like 10 over 6. Then you can see the power of the nucleus. Like this is why the nucleus with this causing problem with this big massive atom is really causing a lot of trouble and a lot of radiation. Because actually, you see, this is for the deuterium, and you think it, the deuterium is a small atom, having practically the proton and the neutron is small and simpler. Then if you begin to put something bigger, it's going to be higher. Then, and also you can see how this quantity is millions times greater than the electron. This means every power is in the mass of the atom. The electron is just going, moving, but the power of the energy is in the center, that is the nucleus. Okay, then in general we have this relation for the different combination. And now another important thing is that, as I told you before, the gamma radiation plus the deuterium is going to be the neutron plus the proton. Yeah, this means when you have dissociation of neutron and proton, in this case you are going to have release some gamma radiation. That is going to be extra. Okay, also you can find some relation between the photonuclear radiation and the reaction that is going to cause is we have the energy of the photon. Then we are going to add this extra energy. We have the same radiation for the deuterium. We have the mass of the neutron, the hydrogen, and additionally we have the kinetic energy of the neutron and the proton to do the balance of energy. And with this, we are going to be able to find how mass is going to be the HF depending on the bonding. And then the experiment are going to show that photons of energy less than 2.22 megaelectron-volt cannot dissociate a deuterium. Then you need more energy than that to dissociate. Okay, another important characteristic here is that the deuterium nuclear spin quantum number is 1, because you know we had the neutron and the proton is 1/2 plus 1/2 is 1. And then they are aligned in parallel and in the same direction. This is why it's 1. If they were in different directions, then we were having 0. The nuclear magnetic moment of the deuterium is 0.86, and the sum for the free proton is 0.88. Okay, after this study, then the scientists begin to think, okay, now we can also see how mass is going to be the